thermodynamics. Now, before we talk about the processes, we should know when a process has occurred. Now, what is process? You can take this down. Process is when a system changes from one state to another. So if a metal is black and you are heating that metal, the metal turns to blue or white. This is an instance, please. The metal is black and you heated the metal and it turns to blue. Process has test what occur, because there is a change from what? From state 1, which is what it was what? Black, to what? State 2, which is now what? Blue. So process has said to what? Occur. In thermodynamics, we basically have 5 processes. In thermodynamics, we basically have 5 processes. The first one is what we call the isochoric process. So processes in thermodynamics, the first one is what? The isochoric. If you are not hearing isochoric, then you hear what? Isovolumic. So the first one is what? Isochoric process. Now the second one is what we call the isobaric process. Isobaric process. I told you they are specifically what? 5. The third one is what we have what? The isothermal process. Isothermal process. The fourth one is what we call the isentropic process. While the last one is what we call what? The polytropic process. So the fifth one is what we call the polytropic process. So general gas constant. Why we are doing that is so we will know how to calculate all these processes. Now let's take for general gas constant, general gas equation. Now the general gas equation that we know is from chemistry is PV is equal to ZnRT. Now, what is our P? Our P is what? Pressure. V is what? Volume. N is what? Number. R is what? Gas constant. General gas constant in chemistry. T is what? Temperature. Now Z is what we call compressibility factor. Where Z is compressibility factor. R is general gas constant for chemistry. Now in thermodynamics, our R here is called specific gas constant. In thermodynamics, the R is called specific gas constant. R. Now, see, when your compressibility factor, which Z, when Z is equal to 1, then it is what? 50. But when your Z is not equal to 1, then it's what? System. Now, but in thermodynamics, we are interested in the ideal system. You understand? Thermodynamics, our general gas equation will be what? PV equal to, we are moving Z, and it will be what? N R bar T. Where R bar is what? General gas constant. In thermodynamics, this one here, R bar is what? General gas constant. While in chemistry, R bar what? General gas constant. But in thermodynamics, your R is what? Specific gas constant. Why R bar is what? General gas constant. But we know that from elementary chemistry, N here, which is number of moles, is equal to what? Mass over what? Molar mass. So we can substitute what we have here into this place. Now substituting this into this place, we have that one. PV is equal to what? M over big M R bar T. Now let's take this mass to this other side of the equation. Taking this mass, what do? We divide 2 by what? Mass. Now dividing 2 by mass. Dividing 2 by mass. Now if you divide 2 by mass, you have what? PV over what? M is equal to R over T over what? Molar mass. Now note, in thermodynamics, to calculate for specific gas constant, which is what? R in thermodynamics. We know that in thermodynamics, your R now is equal to R bar over what? Molar mass. In thermodynamics, note, your specific gas constant, to calculate it, it is what? R bar, which is the general gas constant over what? Molar mass of the particular substance.
This is R minus specific.
So this R is what? Specific. Now from this equation on this left hand side, we can say that our R bar here, this can be written as R bar over L multiplied by T. So let's rearrange this equation here. So if we rearrange this equation, let's see what we have. If we rearrange this equation here, let's rearrange this equation. If we rearrange, we have something like PV over what? M equals to R bar over M, then what? T.
So that's nothing for R.
Okay. So anywhere we see R bar, can we put R? So we can put this R here. But we know that to calculate for specific volume, what is specific volume? Volume over mass. What are we saying? Volume over mass. So substituting that concept, we know that V, small v, is equal to V over what? M.
That is the big V.
Yes, this one here is big V. So substituting what we have here, which is big V. So substituting this, we have P small v is equal to what? What is R over M? Specific gas constant, which is R. So this is the equation we'll be using as this course goes on. We've talked about 5 types of processes in thermodynamics, where we prove the equation for solving what? The general solution in thermodynamics. We said that what? PV is equal to what? RT. Where our P was what? Pressure. V is what? Specific volume. R is what? Specific gas constant. And T is what? Temperature. Now, I gave you 5 processes in thermodynamics. What are they? The first one was what? Isochloric process. The isochloric or the what? Isovolumic. The second one was isobaric process. Isobaric process. Now, the third one was what? Isothermal. Isothermal what? Process. The fourth one is what we call the isentropic process. Isentropic process or what? Reversible what? Adiabatic process. So we have isentropic process or reversible adiabatic. Was the polytropic process. Polytropic process. Now in thermodynamics, you'll be asked to solve for each of these processes. Now to solve for each of these processes, what we first get is what we call the equation of state for our processes. Now to get the equation of state, we what? Apply this what? Formula, which is what? PV is equal to what? RT. Now the first thing to solve, the first thing to get for each of these processes is what we call, one is the equation of state. Equation of state. Now we have to get the equation of state for isochloric process, isobaric process, isothermal process, isentropic process, or what? Our reversible process, adiabatic process. Now for the polytropic process, we will explain what a polytropic process is. But for these 4 processes, we have to get what? The equation of state for the 4 processes. Now, after getting the equation of state, the next thing we get is what? The work interaction. So the next thing is what? Your work interaction. Now, under your work interaction, you will get what we call the flow work, your non-flow work, and your shaft work. So under your work interaction, you have to find what? The workflow, which is WF. The second one is what? Your non-flow work, which is WNF. And the last one is what? Your shaft work, which is WSH. Now, after getting your work interaction, the next thing you get is your what? Your heat interaction. Now, your heat interaction, it is represented by Q. So you have to get your heat interaction, which is Q. Now, under the heat interaction, you might be asked to calculate for what? Your change in energy, change in enthalpy, and change in what? Entropy. First one is what? The first one is change of what? Internal energy, and is represented by change in U. The second one is what we call the change in what? Change in entropy. And we know what is entropy. Entropy is the degree of what? Disorderliness of a system, and is represented by what? Change in what? S. Now the next one which you have to calculate for is what? Your change in enthalpy. That's the total heat for that system. Now the C is your what? Change in what? Enthalpy, and is represented by change in H. Now, let's get the equation of state for these processes. Let's get what? The equation of state for these processes. Now, the first one you can take down. The first one is what we call the what? Isochoric process. Isochoric process. The first one is what? Isochoric process. Now, for isochoric process, your isochoric process is the process where volume is constant. So you can take this down. Isochoric process is that process where your what? Your volume is constant. That is, for isochoric process, your V1 will be equal to what? Your V2. Why are we using V1 is equal to V2? Because sometimes for state 1, your volume, for state 2, you have volume. So the volume will be equal for state 1 and state 2. Now recall that what is our equation we are using? We are applying the concept of what? General what? Gas equation for thermodynamics, which is what? We know that from that equation, PV is equal to what? RT. Where V is what? Pressure. Where P is what? Pressure. V is what? Volume. R is what? Specific gas constant. And T is what? Temperature. Now, for this process, we said what? V is constant. So if V is constant and we know R is constant, can we group the constant one side? Yes. Let's group that one side. We have what? P over what? T is equal to R over V. So you have your temperature, your constant one side, and you have those ones that are not constant one side. Now let's call this constant to be K. So these two constants, but R over V is equal to K. So anywhere we see R over V, we can represent K. So putting that into the equation, we have that what? K is equal to what? P over what? T. Now if you have that, then we have that what? For state 1, because we are having state 1 and state 2. For state 1, P1 over T1 will be equal to what? P2 over what? T2. T1 over what? P1 is equal to what? T2 over P2. This is P1. Now what is the next process? Isobaric process. Now take this down. For isobaric process, pressure is constant. And I said for isobaric process, pressure is what? Constant. So the next one is isobaric process. Now for this process, P1 is equal to what? P2. Now what are we recalling? our general gas equation for what? Thermodynamics. But we know that PV is equal to what? RT. What is constant in this process? Pressure is constant. So can pressure be constant here? We know that pressure is constant. So let's group those constant one side. Grouping the constant one side, let's take this constant to this other side. So we have P over R is equal to what? T over V. What is P over R? Is a constant. So let's say that is, let K be equal to what? P over what? R. So anyway we are seeing P over R, we are representing it with K. So we can say that what? K is equal to what? T over V. Now we know that we are talking about state 1 and state 2. So this can be what? This can be written as T1 over what? V1 is equal to what? T2 over V2. This is the equation of state for what? Isobaric process. Look at this equation well. What is this equation talking about? This is Charles' law. So we can say that for isobaric process work with what? The equation of what? Charles' law. So this is Charles' law. Charles' law. So you can use Charles' law. Remember the what? The equation of state for what? Isobaric what? Process. Now let's talk about isothermal process. The next one. Isothermal process. Isothermal process. Now in this process, take this down. For isothermal process, temperature is constant. For isothermal process, temperature is constant. Now in this process, for both state 1 and state 2, T1 will be equal to what? T2. Now if T1 is equal to T2, what are we looking up to? We know that what? But PV is equal to what? RT. Now we know that for this process, R is constant, T is constant. So can we say that this is equal to what? K is equal to PV. Now if K is equal to PV, what is now the equation of state for this process? Now to get the equation of state for this process, the equation of state will be what? P1 is equal to, the equation of state will be P1 V1 will be equal to what? P2 V2. So this is the equation of state for what? Isothermal process. Now what is this? From elementary chemistry, we know that P1 V1, P2 V2 is what? It is what? Boyle's law. So you can use the approach to Boyle's law to remember what? The equation of state for what? Isothermal process. Now for isentropic process is given by isentropic process, and we know that isentropic process is also called what? Reversible adiabatic process. For your isentropic process, your entropy is constant. For isentropic process, entropy is what? Constant. Now what is entropy? We know that entropy is what? The degree of what? Disorderliness of a system. And we said for isentropic process, what is constant? Entropy is constant. So for isentropic process, we have what? S1 is equal to what? S2. Now to get the equation of state for an isentropic process, we use this formula, which is what? PV raised to the power of what? Gamma is equal to what? K. Where your P is what? Pressure. V is volume. Then gamma is what? Isentropic constant. So your gamma is what? Isentropic constant. While your K is your normal constant. So your isentropic constant will be given to you, your constant will be given to you, or they will tell you to get volume using this formula. Now, but isentropic constant is equal to, that is gamma is equal to Cp over Cv. Your isentropic constant is equal to Cp over Cv, where your Cp is what? Pressure constant, and your Cv is what? Your volume constant. Now the last process we'll talk about is the polytropic process. Now, we don't really regard this polytropic process, because if the polytropic process is a kind of process where if you are not seeing isochoric process, or your process is not isobaric, or your process is not what? Isothermal, or your process is not reversible adiabatic, not what? Isentropic, then that process will be what? Polytropic. Now, to get your polytropic, the equation of state for polytropic which we use is, now the last process which we talk about was what? The polytropic what? Process. And I told you that if your process is not an isochoric, not what? Isovolumic, or what? Isobaric, or isentropic, or what? Reversible adiabatic, then that process is what? Isentropic. Then that process is what? Polytropic process. Now for polytropic process, the formula we use to get our polytropic process is what? PVN is equal to what? K. PVN is equal to K, where your N is what? Polytropic exponential, or your polytropic constant. Now note this, when N is equal to 0, then your process is what? Isobaric. But when N is equal to infinity, then that process is called isochoric process. Isochoric process. Then when N is equal to 1, then your process is what? Isothermal process. Isothermal process. Then the last one, when N is equal to K, when N is equal to K, then your process is what? Isentropic process. So you will be given this formula in the exam, and they will ask you, when is your N said to be an isobaric process? When is your polytropic what? Exponential said to be an isochoric, said to be an isentropic, not what? Isothermal. Use this to give them your answer. Now the next thing we'll do is to talk about the work done, how to calculate the work flow, your non-flow work, your shaft work, your internal energy, your enthalpy, and your what? Your entropy of a given process. Now I will give you a table that will simplify everything you need to know. Now take down this table. So for this first one, this is isochoric process. Isochoric process. This second one is isobaric. This is isobaric process. This is isothermal. Isothermal, while this is isentropic. So our consideration are what? The isochoric, isobaric, isothermal, and the what? Isentropic. Now for the polytropic, I said when your polytropic constant is equal to a certain number or is an infinity, it is any of these processes. That's why we are not considering the polytropic process. Our aim is to consider what? The isochoric, the isobaric, isothermal, and the isentropic. Now for the isentropic process, we know that isentropic S1 is equal to S2 for this process. Entropy is what? Constant. For isothermal, temperature is what? Temperature is constant. For isobaric, pressure is constant. While for isoporic, volume is constant. Now I told you for each of these processes you'll be asked to calculate for what? Your work interaction, your heat interaction, your change in U, your change in H, and your what? Your change in S. I've given you a table that simplifies whatever you want to calculate, whether what? Your workflow, which is this, your change in Q. This Q1 to means heat interaction for process 1 and 2. These are the formulas you use to calculate for heat interaction for any of these processes. Now, we have what? The non-flow work. I've given you formulas you use to calculate for your shaft work. This is for entropy, this is for enthalpy, while this is for what? Change in what? U, which is change in what? Internal energy. Now, you can use this table to calculate for any of the processes given.